Okay, can people hear me if I'm talking like this? Super, okay. So hopefully you're expecting to be here for FTorch and not testing, which is excellent. Away we go. So I'm Jack, and I'll be delivering this session along with Joe, who's just had to pop out for a moment, but went back and did the automatic differentiation for you. And we've got a couple of people floating around to help as well. So I think Tom is at the back, and Nico is also somewhere. I think he's over there. So the sort of the structure of this session is going to be a little bit of kind of background information for those who maybe aren't so familiar with the FTorch work and the software that we've been developing. And then we'll go into kind of some practical exercises of actually using this and seeing what we can do with it. But the main thing to take away is that this is software that we've actually developed at ICCS. So we are kind of the developers and maintainers of this. And its objective is to sort of facilitate coupling of models that people have developed to do kind of machine learning applications, with the hope of then combining those within larger models. If those larger models are written in Fortran and your machine learning applications are written in PyTorch. So before we go too far, you're going to want to go to the repository for this workshop, which is possibly on Slack, but if not, maybe Tom can drop it in there. And I should just highlight, this is not the FTorch repository you're going to, this is the FTorch workshop repository. So just make sure you end up in the right place. You can also get there with the link from that, or from the QR code just there.
I'll put it inside now.
Super. And so I'm going to hope that everyone has had some time to digest that. And then we'll move on. So if you are on the GitHub workshop now, the GitHub repo now, we're going to run this workshop within code spaces. So I think if you were at any of the AD sessions, this would be similar to that. And possibly a couple of the other workshops as well. You probably noticed that this does take a little moment to kind of get set up. So we'll do that first of all, then we'll have some slides about FTorch before we go on to continue the workshop. So if you are on the repository page, it will look something like this. And if you go to the green code button and drop down, and rather than the local tab, click on the code spaces tab, and then you'll find there should be a green button under there to create code space on main. So here we've already set one up, ready for the workshop. But if you click that green button, it should open a new tab and start doing some things to get yourself set up. If you leave that churning away, once it does get set up, you'll want to just run this command in the terminal it drops you into. So source build FTorch, it's a shell script. And if you want a copy of these slides, because we're going to move on, you can find those. They are linked from the repository in the web link just over here. So you can follow along in your own time there. Okay. Any questions, or are people happy sort of getting that going in the background? Super. If you do have any problems, just stick your hand up and one of our wonderful helpers will come and sort you out. Okay, so I've sort of hinted a little bit about the motivation for this work, but kind of to make it clearer here, we have machine learning and we're using machine learning science. Sort of often, and I'll use machine learning and deep learning interchangeably here, but often when we think about deep learning sort of in a traditional sense, it's often in an end-to-end capacity. So we have some kind of inputs and we're running this sort of input through a neural net to generate some kind of output, and then that output is what we want to use in a human sense to say something, do something, one of those. So this is perhaps slightly different. And so I should say, people who are maybe familiar with kind of those weather forecasting machine learning models, this is very much kind of the sense in which they're operating. So they're taking some series of inputs, churning through, doing everything to generate some kind of weather forecasting output. Whereas sort of the machine learning applications that we're specifically trying to target are much more where you're keeping a lot of the numerical model in place, but maybe only replacing one part of that with a machine learning component. So this is often what people might refer to as hybrid modeling. And we're saying rather than replacing kind of our entire system, we're looking at just replacing one part. And that might be because it's a very computationally intensive part, and we believe that we can speed it up using machine learning. So for example, in our climate model here, we know that, say, radiation tends to be a very, very computationally intensive process. If we can emulate that with a neural net and do it much, much quicker, then there's an advantage here. Alternatively, it might be because we're saying we know there's a lot of complicated things, such as in convection, which is underneath here, and we say that our models, sort of the assumptions we make, can only take us so far, but we've got a lot of real-world data out there. If we could perhaps construct a model that learns from this real-world data, we'll actually get better representation of that process within our model, and it will improve the predictive capacity. And anything sort of along this spectrum, you can think of both. And there's other applications as well. However, there's some challenges when we come to do that. So things that we've perhaps been talking about this week with some of the software principles, there's the reproducibility. So if we've kind of trained a model somewhere away from our much larger climate model, we want to make sure that the net's going to perform exactly the same as it did away where we trained it, as it does when we plug it back into our larger climate model. There's also kind of a principle of reusability here. So we want to make parameterizations that we're developing as widely available as we can. So perhaps we deploy something for convection within, I don't know, the sort of, maybe we develop something in ICON, which is the German weather model, but it would be really nice if we can then redeploy that same parameterization within, say, the unified model of the Met Office, or maybe WRF developed over in the US. But sort of this is not easy to do, and especially for machine learning schemes where a lot of the inputs are fixed. So kind of you've got an input tensor, which will be sort of strongly tied to the grid of the model that you've trained it on. If we can make it easier to kind of facilitate that reusability, that would be the thing. And then the final thing, which really FTorch is targeting, is the problem of language interoperation. So I guess as a quick show of hands, how many people have been sort of looking at developing machine learning components for models in some of their work? Yeah, and how many people who answered yes to that have been using something other than PyTorch or TensorFlow? Okay, are you using JAX or? Yeah. What are people using?
Oh, I mean, most but yes.
Okay, but the model is still developed in PyTorch, right? So yeah, most people are using PyTorch, but the models we're trying to bring them in sort of won't be PyTorch, won't be Python. They'll be written in some higher level languages, and so there's a challenge of kind of matching these two up to get them to talk to one another. And that's exactly what's depicted here. So a lot of our machine learning, our training is done offline somewhere in Python. Weather models, our ocean models will be written in some sort of high performance compiled language, most often Fortran. I'm hard pressed to think of many weather models, climate models, ocean models that aren't, though there are some out there, I'm sure. And so like I say, the challenge is kind of marrying these two up or providing a bridge from what we've done in Python, allowing us to run it within the Fortran effectively. So this is kind of the problem that we're looking to solve with FTorch. But there's kind of two types of efficiency that we're concerned with here. So there's the first one, which is the computational efficiency, which is perhaps what we think about when we say efficiency in a software context. So how fast is something going to run? How much data is it going to consume? What's the memory required? We want to kind of write some software that will handle all this in the most efficient, lowest resource way possible. But there's also the developer efficiency that we need to consider, particularly within the context of research and research development. So when we're looking at kind of coupling work that's been done in PyTorch to models that have been developed in Fortran, this is often being done to kind of answer some kind of scientific question. And so we want to facilitate sort of answering that scientific question, doing the simulations, exploring the parameter space as much as we can, rather than having people sort of getting bogged down in sort of the nuances of computational development, programming languages, sort of memory management, all of this side of things. So it's sort of this dual goal we have in developing this software, which is doing it in a computationally performant manner, but also in a way that's kind of easy for researchers to use, easy for non-technical specialists to be able to sort of pick up and use within the code they're doing to facilitate that research. So moving on slightly, so before I move on, are there any questions at that point that people have? No?
Has everyone got the code space for it?
Does anyone not got it one?
Yeah.
And have people run the source shell script command if they've got it loaded? Super. So moving on a little bit, I think it will help before we start on the workshop to understand exactly what we're doing here. So we'll start with PyTorch, with which you're hopefully all now familiar after Matt and Isaac's great workshops. So this is a framework for doing machine learning, specifically deep learning within Python. But what's worth noting here is that the reason this is kind of so quick and so efficient is that whilst you use it in Python, it actually runs a lot of compiled C++ code underneath. And this compiled C++ code is actually kind of its own little library called libtorch. So whilst Python kind of gives you this interface, it is possible to go direct and run the C++ compiled code, though it's a bit more restrictive and there's maybe fewer features than some of the Python things that are in there. But the important thing for us is that Meta, who developed PyTorch, provides this kind of C++ library as a standalone binary. And it has the ability to read models that have been saved from PyTorch and then run them just through C++. The key bit for us is then that we can write code that will use C++ routines or call out C++ files from within Fortran. There's this nice module that was added as part of the 2003 Fortran standard that allows you to make calls out to some kind of API written in C or C++. And so that is exactly what we're going to do. So the traditional route sort of people might have been thinking of taking previously is if you've got some Fortran over here and you want to run some PyTorch model over here, is you'd have to make a call out from Fortran into some Python. That Python would then have to make a call into some PyTorch to run the model. That model would have to place the data somewhere and send it sort of back up the loop, back through the Python, and then that data would have to be read into Fortran somewhere. And with that Python runtime, you've got the whole kind of problem of managing your Python environment. So we spoke a little bit about virtual environments and that these are nice for kind of specifying dependencies. But we also said that another reason to do this is because different programs will run with different dependencies and it allows us to compartmentalize. If we're wanting to run something on kind of a standardized system, for example, a high performance computing system, or a departmental cluster where that software stack is being managed, actually controlling that Python environment can get quite messy. And I think XKCD had a wonderful sketch about Python environments showing this challenge. And so there's a desire, if possible, to kind of avoid using all of this Python ecosystem and just use PyTorch directly from Fortran. And indeed, that's what we are doing. Is by writing Fortran that will call directly to the C++, we sort of negate the need to go through all of this mess and ecosystem over here. So that's been kind of a very quick whistle-stop tour because we're keen to get on with the workshop and the practical side of things. If you do want some more information, there is a talk that Joe and I delivered last week that was an hour-long discussion just about the development and the applications of FTorch, and you can get those slides there. And there'll also be another seminar, I think, next week, if you want to hear more about this. But at that point, before we move on, does anyone have any questions on kind of the functionality? Or anything that wasn't clear? Okay, in which case we'll move on to the practical. So hopefully everyone's got a code space up and running and you've run that build script. If not, do stick your hand up and someone can help you. But we're going to start just with a quick check of sort of who's used PyTorch sort of in their work and is comfortable with at least running PyTorch machine learning models. Okay, super. And how about Fortran? So who's used Fortran to write compiled code using it running maybe numerical models? Ooh. Who's done both? And who's done neither? Okay. So the first thing is just going to be a kind of a quick example to make sure everyone's up to speed. Some of it will be easy, some of it will be maybe less easy. But what you're going to want to do is within that code space here, and I think, have you run? So I've been telling you to get ready, but in fact, I have not. So if we run the source script, it's going to go away and create a virtual environment, install some of our dependencies, and then build and install FTorch for us, making sure that everything's ready to go and ready to run. What I would encourage you to do is now go to the exercises. And if you look in exercise 0, this is kind of just our leveling exercise. And we're going to start off with the Hello PyTorch example. So if you look in here, this is a little script or a little piece of code that's going to define kind of really simple PyTorch neural net. We've called it SimpleNet. It'll look familiar if you're in any of the introduction to ML. And you can see here that rather than doing anything complicated, we're just defining a single linear layer, and we're actually explicitly setting the weights so that this linear layer is not an eigenvector, it's a identity matrix that's going to multiply whatever input we give it by 2. And then we've got a forward method, which is simply going to run this linear layer on some input vector that we give it. At the bottom, you'll see that we've got one of these magic methods. So if we call this script, it's going to take some input tensor that we define here, 0 to 4, pass it through the model, and tell us what the input is, what the output is. Hopefully it will be multiplied by 2. And if we so get rid of this. If we cd into exercises and exercise 0, hopefully we can do. And is that big enough for people, or do you want me to blow the text up a little bit?
Yeah,
Let's do Control+. Yeah.
Super. So what we should now be able to do, because you can see on the left here, we're in this virtual environment where we've installed dependencies, Torch, NumPy, whatever else. We should be able to call Python and then this Hello PyTorch script. And indeed, we can see that the input tensor, after passing through the net, has been multiplied by 2. Anyone, any questions at this point? Anyone not managed to run that?
Other reasons.
Okay, super. So we're all happy with PyTorch. The next thing we'll move on to talk about is Python. Is Fortran even. So here, the one thing that we've done when you ran that script, it will have installed some of the things that you need to do this. For using FTorch, it is compiled code. It is going to use Fortran to talk to C and C++. And so you're going to need compilers for these languages. So we're using here G-Fortran, GCC, and G++, which is the GNU compiler suite. If you want to use in your work, say the Intel, either the old or the new Intel compilers, that is also an option. And the way you can check that these are on the system is just to run a quick check on the version. The other thing that we're going to need to do this is CMake. So who is familiar with CMake or has used CMake before?
User.
Okay, so CMake, you can think of, we sort of touched on packaging in the RSE skills session, where we talked about sort of it making it easier to pull dependencies in, easier to distribute software and build and install software on different systems. And this is exactly what CMake does. So sort of the old Dark Ages way of doing things would be you provide a make file with your code, and you can run your make file on your computer. When you give it to someone else, sort of the installation instructions go something like, look at the make file and try modifying it. This is the problem that CMake sort of looks to resolve. So it has inbuilt ability to go and search for the various dependencies on your system, be they compilers, be they a netcdf install, be they NPI, and it will do its best to kind of pull all those in, then construct an appropriate make file for your machine without you having to do so, and then allow you to build the code. And again, we can check this is installed just by doing a call to the software followed by a check on the version, which would look something like, say, if we want to check version, there we go, we can see it's there. And if you're trying to use this sort of at a later date, and you find that you can't find the necessary things, there's either instructions for these online, or you can speak to kind of your system administrators who should be able to help you with obtaining them. So moving on to the Fortran in that code, in that file, or in that directory, sorry. If we take a look at the hello Fortran, you will see this defines a Fortran program. So this is done helpfully with the keyword program. Then at the top, we have to define all the variables that we're going to be making use of in that program. Because Fortran is a compiled language, we can't kind of define things on the fly like we would with Python. And instead we instead we need to define everything up front so that the compiler knows to create these, allocate the memory for them before doing anything else.
Just installing some syntax now. We hope that will look better.
Excellent. Thank you very much. So yeah, and then we have some things we can do. We can print some inputs and outputs. The other thing to highlight here is that we've also got this mathmod file. And so whilst the program in Fortran here perhaps looks rather sparse, what we can do is put code in other files, and then when we compile them, we can bring them together to join to form one larger piece of code. So actually much of the work that's going to be done is in this mathmod, which is in Fortran is module. And so you can see here that we define just one function, or one subroutine, sorry, which is multiply by 2. So this code is going to fulfill a very similar purpose as our introduction to PyTorch, except that it's going to be doing it sort of the way you might expect, which is simply multiplying by a floating point number rather than doing it with a neural net. So it's slightly more complicated, or well, slightly more legwork to get this into something that we can run. The first thing that we've got to do is take this command here, where we're going to call our G-Fortran compiler, and we're going to tell it to compile both the mathmod file and the hello Fortran file into some kind of machine code. So if you copy that, we can put it in.
It often doesn't like pasting into this VS Code session.
Oh well, I'll have to type it.
Browser thing. Section.
Oh, okay. I've not done that, unfortunately. I think you need
And
to
there
compile.
was, you're exactly right. Because the math module is going to be used by the Hello Fortran, I think we probably need to put that in there first. So if we run that, hopefully you will see that this has now produced some files with the same name, but a .o and a .mod. These are kind of the intermediate files in the compilation process. So what's happened is Fortran has turned them into machine code, placed them on the system, but it's still not created anything that we can run yet. So that comes in the next stage, which is called linking, which can be done again with Fortran. This time we tell it to produce, to take these separate .o files and combine them into a single executable that we can then run on our system. So we're going to say Fortran with the -o flag. We're going to give the name of our program and then the name of the files that we want to be combined. So Fortran -o, and we will call it
prog.
yeah, I can't remember exactly, but as long as you're consistent, we'll be okay. And then we want the .o file and you'll see after we've run that, we've now got this executable, Fortran prog has appeared, and all things being well, we can then // so that the command to run that executable, run Fortran prog, and sure enough, we've got something similar, taking that input vector, multiplying it by 2. Are there any questions on the Fortran side at that point from anyone? Yep. Yeah, a good question. So when you compile, it's a feature of Fortran that when you have a module, it will produce both the .o file and the .mod file. And Tom is going to correct me because knows far more about Fortran, but I believe the .mod file contains kind of readable information about the functions within the .o file, whereas the .o file is just kind of that machine code that gets linked up.
Actually, human brain the mod file.
It's probably not. It's like it finds the interface, like the types that it expects. These things are
Okay.
Yeah.
Intermediate.
Yeah, so it's human readable with some command line tools. But yeah, it's a good question. Yeah.
I just tried and you can't.
Yeah, and it's worth saying when we sort of say it's this intermediate interface, it's not it's not useful. You can always regenerate with the compilation, so you don't want to kind of ship it around with your code. Is also worth clarifying. And the other thing to say here is, so we've been through and done all of these stages sort of step by step. This is to kind of give you an understanding of what's happening underneath a little bit. But if you were using CMake to build your code, CMake will actually, when it's found the compiler and it's looked at your files, it's intelligent enough to process your files, figure out what depends on what, and it will actually construct these commands and insert them into the make file for you. So for the rest of the workshop, we'll just be running CMake, but just be aware that this is what's happening underneath when we do so. Okay, there we go. We run. So then very briefly, like I say, we've installed FTorch for you as part of that source FTorch build script, because we kind of want to get on with doing some interesting things. If you want to do this on your own system, just a couple of things to be aware of. So the main source code for this, if we look at the FTorch repository, is contained within, let me see if I can open this. Oh. So the main code for FTorch is contained within the source directory, and it consists of really this ftorch.f90, which is the Fortran interface that we'll be using today. and then is the ctorch.cpp, which is kind of the intermediate layer that goes between the Fortran FTorch and the C++ binaries that are provided by libtorch. And then built around that, like I say, are sort of some of this CMake infrastructure to make the process of installation easier. The other thing that's included in the repository is sort of there's a lot of exercises. So these are kind of what we'll be working through today, but then there's far, far more on there that are designed to take you through kind of all the different steps of doing things, for example, using MPI or using GPU acceleration, doing some automatic differentiation, or this sort of thing. So we've talked about CMake and we've talked about how it would be built. And so I would suggest if you want to have a go at this, either book a code clinic or come and speak to us, or you can have a look at you can have a look at the build FTorch script that's part of this workshop to see what commands were run to do that. But we're always happy to help people working with installation. So I think we'll move on to the exercises at that point, and I will hand over to Joe. There we go. Turn it off.
Okay. Yeah, so we've done the sort of hello world exercise, and then we're going to revisit that same simple net that was all it was basically doing was multiplying by 2, but we're going to look at it more in the context of FTorch. And so this exercise number 1, and we're basically going to go through the workflow of how people use FTorch typically. So I think we might have some diagrams actually that I might skip back and forth because I find them quite useful. So this is the kind of schematic that we've got of the workflow of how people tend to use FTorch. And for those of you that know a bit more about machine learning, this is the offline approach. So you can do offline training and online training. We can maybe talk about online training later if there's some time. So in this standard approach, you design your machine learning model in PyTorch, similar to how it was done in Matt and Isaac's course. So it's the natural way to do that is to do it in Python. So you do that, and then you will do the training in the same way as you would do as well, like we see in that course. But in order to do the training, you need some training data. So we've got this machine learning model. We've also got a Fortran model, which is the thing that we're trying to emulate part of. It's kind of the main use case that people have is that the part of their Fortran program that they want to replace with a neural network or some other machine learning method. So we need to run this code a few times to generate some data, and we store that to a file. Probably use this thing. So given that you've done that, you've run the Fortran model a lot of times, generated some data, you can do your training, and as in the other course, we produce this PyTorch model file, so it's like model.pt or whatever. Jack mentioned before that we have a slightly different format that we need to use. So it's called Torch script. And basically within FTorch, we provide a utility called PT to TS, so PyTorch to Torch script, that allows you to convert these. And then once you've got that, we can do the sort of model inference in Fortran, but we'll have to make some code changes. So we're going to go through all these different steps. Well, maybe not all of them, but we'll go through at least some of these steps so you can get an idea of what we're going to do. So this one, the training one, we're not going to do because it's not really too relevant to what we're showing you. It's all just PyTorch type stuff. So we've basically replaced the training with having a very trivial model that doesn't need training because it already gives you the right answer. But all the other steps we're going to go through. And so yeah, it's going to involve designing and training the model, saving the model to Torch script, like we just said, writing Fortran code that uses FTorch to call the save model, and then we compile and run the code, linking it to FTorch. Does that make sense so far? Just sort of in abstract. It would be a little bit more concrete as we go through. Okay, so you can navigate to this exercise 01 location, and we'll find this Python file called simplenet.py. And this is almost exactly the same as what we just saw before. I don't know that there's really any noticeable differences. But if I open this file here, I'm just going to close the old exercise. So yeah, again, it's very similar to before. We've got this simplenet class. We define basically a scale. It's a linear layer that's just going to be a scaling of the identity matrix, and we define this forward method. And then at the bottom, you can see there's a bit of code that will do the same things before. We read in an input vector, we run the forward code, and then we print out the result. It's pretty much the same as before. And we go to the right location, so exercise 01. We should be able to just run this simplenet.py, and we get it. This time we're only printing the output, but it gives the double the input. So hopefully that's fairly trivial. And then the next bits will be a little bit more involved. So I'll keep flicking back to this so we can see whereabouts we are, but we've designed the ML model basically, and I'll leave you to look at it in more detail if you would like to. And as I said, it's already technically pre-trained. So I mentioned that there's this utility called PT2TS. So there's a template for this that we provide in FTorch, and then you have to modify it slightly for your use case, because you're going to need to pull in your machine learning model, and you might have like different numbers of inputs or outputs that you might need to account for. And so this is the template, but we've got a different version that's going to be shown in the directory. So it's already been copied over to exercise 01. And we've left in some to-do comments, which are basically the exercises. This script expects this neural network module, which is the simple net that we just mentioned. It's got this forward method. And there's these two different options, tracing and scripting, for how you save it. And we're using the scripting approach so we can get torch script. If anybody wants to know a little bit more about these differences, then put your hand up and we can have a chat about that. And you can summarize the torch script model from Python as well. So we go to here, then I'll show you what the exercise is going to be. So we've got simplenet.py, and then we've also got PT2TS. And you'll see these to-do notes. So FPT lib, so I guess Fortran PyTorch lib, maybe that stands for. And that's the first exercise. Add a module import with your model here. So it's going to be import something. And then as we scroll through, I think there's maybe about 6 of these exercises. It's just an opportunity for you to just dig around and figure out what the right syntax should be. So some of them, it will just be looking at the simple net. Some of them, it might be using some of your PyTorch knowledge. And then for other ones, let's see what the ones there are actually. So yeah, we've got one here, loading the model. So I think mostly it's just knowing what PyTorch syntax is. And for those of you that aren't familiar with the PyTorch syntax, you can actually get the solutions. I would encourage everyone to give it a go, or at least a guess before you look at the solutions. But if you click on the README, then you can render that as a markdown if you click one of these buttons. So it gives you the preview. And then as you scroll down, you can see this is the first Python task. And then if you click this button here, it will show you the answer. So we'll leave sort of 5 to 10 minutes for this, just to work through the PT2TS file. and to go through these different exercises. So you can, there's going to be 1, 2, 3, 4, 5, yeah, 6. There's 6 different tasks, and then there's going to be some similar tasks for the Fortran as well. Does that sound okay? All right. Yeah, just a note that you won't be able to run the PT to TS script until you finish the exercises. It will give a crash because these different comments that we have are things that need to be implemented. I think if you only do a subset of them, it might work, but it probably won't give you the right answer or do the right thing. So, yeah, you'll need to go through the tasks first, unfortunately. So I'm just going to go through the first one, just so it's a little bit clearer what's going on. So we're actually going to be editing the PTTS script. So there's this first to do here, which is at the very top. It's a comment. And it says add a module import with your model here. So we're actually going to add another line of code here. Does anybody know what it's going to be?
Import SimpleNet.
Exactly. SimpleNet is the name of the module, the Python module. And so we just, all we've got to do is just type that. And then if you want, you can get rid of that. It's up to you. You don't need to get rid of comments. But and then if we look at the solutions, it will show you that. Okay. So for the second part, we've imported the SimpleNet module, and then we need to finish this line of code here. So we've got train model equals something. Does anybody have a suggestion for what we put there?
SimpleNet.
Exactly. So we need to instantiate the model, and again, the trained bit here is a little bit of a misnomer, but it's such a trivial network that it's already pre-trained. Like we've already got the right answer. So all you got to do is just create this thing. So as we go through, I'll also make changes in the code so that we're able to run the code.
Okay. Okay.
Yeah, I guess in the interest of time, we'll sort of go through a couple more of them. The next one is only a single character that we need, which is quite nice. Does anybody know how we finish this here? So we've got the train model dummy input. We need to create some input. It's being chosen here just to be all ones. How do we finish this? What's the dimension that we need?
5.
Exactly. So the input is just a vector at length 5. So all we're going to do is just put the number 5 there. So I will go to the right part of the code here and put that 5. So this is like when we saw before, 0, 1, 2, 3, 4. And then having done that, there's a little bit of boilerplate code that we include in here in the case where you're not running on the CPU. But because the code space that we're using is CPU only, we don't need to worry about that. But if you want to use FTorch in your work and run on GPU, then that would start to become relevant. We then want to run the model. So do people recall from the PyTorch course how you would do that? If you've got a model and you've got some input, how do you run it?
Callable, so they just use the object as a function.
Exactly. You just got to call it. So, oops, that one's the one we've already seen. And then here we see that the output is just equal to the train model times the input. I'm just going to try and copy and paste this. Might be slightly quicker. There we go. The formatting is and then we want to save it. So first we need to create the file name. So I mean, you can basically choose whatever you want here. Well, let's just be consistent with the solutions. So it says save model.pt. So we'll just copy that. And then finally, there's the part here that's about saving it to the file. So we've got to fill in the dots here, script to torch script. Hopefully it's clear that all we've got to do is just give it the model and then give it the file name. So this is a slightly different signature to what you would see you're normally using PyTorch, because typically just when you're working in Python, you don't need to worry about the scripting. You would just use model save. So it's slightly different. But then hopefully once you've done that, we should be able to run PT to TS because we've finished all the exercises. It prints some stuff to the screen. There's no errors. And then now we've got this save model.pt. And a bit of confusion perhaps, because we said that we converted from PyTorch format to the torch script format. We're still using the same extension, but this is something that's now readable from FTorch, even though it's got this PT extension. Yes.
Why are we having dummy inputs and so? I mean, the intuition for having a dummy.
It's okay. So the question was, why have we got these dummy inputs?
Just to make the run and do a sanity check.
So it's if you're so the first one is a sanity check. So you'll see at the bottom, we do a very, very quick sanity check, which is double the inputs and check that the model responds accordingly. But the other thing is, Joe mentions the difference between scripting and tracing. Scripting will take the PyTorch code and turn that into a script, whereas the tracing will just take a matrix or take a tensor, pass it through and trace the operations. And so it can be more efficient, but the downside is that it won't catch any conditional stuff in your code, which is why we, I think, opt for tracing here as kind of the safer one, but that is another option, but you then have to run the model to do it.
Yep. Yeah, if you go right down to the bottom, there's some sort of checks as well, like basic checks that is produced output and whatnot. Any other questions about this? Yes.
Very basic thing. So is PT still a conventional file extension for the torch script version? I thought it was going to be TS or something.
Yeah, the question was, is PT a conventional extension for this format? Yeah, I believe so. I've never seen .ts. I mean, you can still read this in PyTorch. Yes, that's on fine.
Yeah.
Okay. Yes, it's Tom just said that PS and TypeScript
PTS.
or PTS. Okay. Okay, we'll move on to the Fortran side of things now. So we've now saved this model and we're going to use it. So there's about 6-7 more tasks on the Fortran side now. So this is going to be adding in some FTorch syntax. And FTorch has been written in such a way that hopefully it feels familiar to both Fortran developers and PyTorch users as well. So we've tried to keep the names fairly similar. So I'm aware that not everyone is too experienced with Fortran, but the first task in this one is going to be to, again, add a line of code after the comment, which is for importing FTorch. So that you don't use import in this case. I will leave you to give that one a go. And we're going to be working with this simple net underscore Fortran F90. And yeah, the first to-do note is there. One thing that might be useful, which I'll put in the in Slack in a second, is if you look at the FTorch web page, so it's the Cambridge ICCS github.io/FTorch, then you'll get there's a load of information in the user guide, which might be beneficial in general. But then also, if you scroll all the way to the bottom, then there's some API docs. So Jack mentioned before about how we've got these different source files here. So there's some C++ files, and then there's also FTorch.F90. If you click on that, then it'll show you the source code. But then also, if we click on the FTorch module, then it shows all of the different things that are in there. Now, the reason I'm mentioning this is that for some of the exercises, you might be just looking for the name of the equivalent. You know, you've got a function in PyTorch, what's the equivalent subroutine in Fortran? So if you scroll down here, you should see thing that you might be looking for. So I don't know, something like this. Yeah, so we've got half an hour left in the session, and there's at least one other exercise that we'd like to look at after this that will be useful for people. So we'll go through a couple of these. Does anybody have a guess as to what we need to type here to import FTorch? Exactly, yeah. So in Fortran, we use use as the keyword, and you can see that just above actually. So you put use FTorch. Now, if you look at the solutions, then you'll see that it's actually saying that you can import. So use FTorch only, blah, blah, blah. That's the equivalent of saying from FTorch import all of these things like in Python. So it's generally good practice to only import the things that you need. But given that you are using FTorch for the first time, it probably makes more sense for you to just put use FTorch. And also you don't, because you've not done the other exercises yet, you don't know what you need. So you can just put use FTorch, but then also if you look at these solutions, then that's another place that might give you a bit of a hint of the kind of things we're going to need for the other exercises. Yes, the question about how these imports work. So, I mean, when you're compiling the code, like Jack mentioned before, you have to link together the different modules that are being used, although CMake might do this for you. But once those are sort of available, yeah, within the code, you can just use this thing. And whilst in Fortran, you have to declare all of the variables that are being defined within that file, you don't need to declare these other things. Like you can just pull them in, and their types and their values are going to be, right, if they have any values, their types and what they are is going to be inferred. And in most of these cases, they're actually subroutines anyway, so we're not pulling in data necessarily.
But that's exactly why it's better to do this, because you can imagine in FTorch, we might have defined something called @tensor. But if you've just pulled that in with all of FTorch, you may also write a subroutine that you choose to call @tensor.
Yeah, this is what I've wondered, because if you might just call it by names, you obviously have multiple modules there.
Yeah.
So by doing this, kind of you're making sure you know what you pulled into your namespace.
Yeah, so if you just put use FTorch, that's the equivalent of saying from FTorch import star in Python, which as Jack just said, like there's a slight danger that you might pull in something that you weren't expecting or overwrite something that's been defined. So the structure, for those of you that haven't seen much Fortran before, the structure of a Fortran program is that you have these imports at the top, like you would do in Python, although it's a bit more strict. So you have to have all the imports at the top. You can't just have some random import like halfway down the program like you would be able to in Python. And then you have the declarations of the variables that you're going to use. So here, we're not giving them any data yet. We're just saying what are they. So you need to specify like integers and real numbers. And then if it's an array, then you need to say what the dimension is. And this is one of the notations for doing that. There's not really scope to talk about what this target means, but if anybody wants to know, we can have a chat. And then so there's a couple of exercises here that are about declaring more variables. And then once you finish declaring all the variables, then you actually have the sort of code. Like, so that's where you start assigning values and calling different subroutines and things like that. Hopefully that makes sense to people. So yeah, there's going to be 2 exercises for declaring things, and then the rest of them are all about like actually writing code that uses FTorch. Yeah. So in the interest of time, we'll sort of go through the next 2, and they're probably some of the harder ones because requires a little bit of digging. So we need to set up the torch data structures, and what that means is that we're we're setting up the FTorch equivalents of the torch tensors for the inputs and the outputs. So did anybody find what needs to be done here? What's going to be their type? We've got some real numbers, we've got some integers. What is the type of the data structures? Yes, torch tensor, exactly. So when you've got in Fortran, if you've got a sort of custom type, then it's called a derived type, and the way that you declare it is using type and then brackets torch tensor. So these things have been pulled in from FTorch. So if you look in more detail here, you'll see that we pulled in torch tensor and also torch model. So when we create the tensors, we use this torch tensor data type. I'll discuss the dimension one in a second, but we've got input tensors and then output tensors. And then for the model, it's just a type torch model, and it's called torch net. Now, the reason that we've got dimension one here is that often when you have these kind of PyTorch models, you have multiple inputs and multiple outputs. You don't necessarily just have like one big array you're passing in and one array that you're passing out. And so to account for this in FTorch, the model class is going to expect an array of torch tensors, and it can produce an array of torch tensors. So what this means is that we've got an array of torch tensors, but it's only got one entry in it. So it's kind of like a trivial array. So this is the way that you would define those. And we can copy and paste that into here. And then to set the torch script model path, this one's a little bit of a tricky one because it requires you to know some Fortran. And rather than asking anyone to spell it out, I'll just show you. So when you're declaring strings in Fortran, you use a character and then give it a length. So 128 is far more characters than we need. But so long as you have more characters than the thing that you're trying to write, that should be fine. So we create a character string of length 128, and we just call it save model. Now you might notice that there's this ... here, which means that it's going to be looking in the directory below where we currently are, or however you want to think about it. The reason for that is that we will build. It's a common convention that you would build the Fortran source into a separate build directory. And the build directory is normally just like called build from the current location. So looking here, we've got these different programs. When we run the Python script, we run it from here. But when we run the Fortran script, we create a build directory like that. And we would compile the code inside there and run it from there. And that means that the PT script, PT model that we created before is not in the right place. So you need to make sure that you've got the right path. So you kind of need to know where we're going to build it in order to get that one, unfortunately. Does anybody have a question about that? Okay, so we can go on to the next bit, and I'll just ask the audience for most of these. So who found out what we need to use to create the input and output tensors from the arrays? So we've got some arrays, we want to associate them with tensors. What's the API call that we need? We can scroll back up to this here. So we've used torch tensor and torch model. Those are the types. Any guess which of these we're going to use to associate a tensor with an array? Yes. Exactly, torch tensor from array. Yeah. So this one, the nice thing about this one, oops, that's another close. The right thing about this one is that we don't copy here. So one of the sort of optimizations that we use in FTorch is that when you have this tensor that gets created, it's going to point to the data that's in this Fortran array. So as soon as we modify Fortran array, it modifies the torch tensor, and as soon as we modify the torch tensor, it modifies the Fortran array. So we don't transfer any data. Well, when we go between the Fortran and the C++ code, there's no data copies. We're just operating on the same data. So we can take that and we can put it in here. Loading the ML model. What API call do we need? Anyone? So let's look back.
Maybe torch model mode.
Torch model load. Yes, that's correct, Jeff. So the idea, if you see here, we've got this torch model, torch tensor, and we're just sort of adding bits on the end that are hopefully in line with the PyTorch syntax. So in PyTorch, you would have load, and here we've got PyTorch model underscore load. So as we go down, load ML model. It's worth noting that both for this one and for the tensors, you need to specify torch kCPU. So we're specifying what device this thing is going to run on. We've made this explicit just so that if someone is running on the GPU, they don't accidentally set it up on the CPU, because that could cause some performance difficulties. So the first one, we're associating with tensor with an array and saying it's on CPU. And then for the model, we created a model, giving it a file, and also choosing a device. And for the next one, I'm not going to ask you what the API call is because it actually says it there in the comment. We're going to use torch model forward. So just to look at the solution, we've got call torch model forward, and then we're basically just giving it everything that we've set up. And that's the model, the inputs, and the outputs. And then we're going to print the output. The last one is actually optional. So we've set it up now so that all of these different models are deleted when they go out of scope. But it's generally good practice when you are allocating memory, which is effectively what's been done here. We're allocating memory for these different objects. When you don't need them anymore, it's good practice to remove them. So this can reduce the memory footprint and avoid you having any sort of potential bugs later on. So the way that we do that, as I showed you in the API docs before, there's this thing torch delete, and you can apply that either to a tensor or to a model. It's overloaded so that it works in both cases. So we can put that there. Okay, and so we've completed the exercise. The next thing to do is to check that it runs. And so I think we've probably got a slide on this. Yeah, there's also this simple net Fortran sol if you want to see the full solution code. To build it, as I said, we create this build directory. We then need to navigate into the build directory, and then we use cmake ... So cmake to the source directory. So it's going to run cmake in that location. Normally, you would also pass in the path to FTorch, but for the sake of this code space, we set it up so you don't need to worry about that. So we've created the build directory, we navigate into it, and then we go cmake ... And you'll find that we've now got an executable. No, we don't. I also need to build. Sorry, that's not in there. We also need to put cmake -- build and then dot. So you'll then see, sorry that that's not in the slides. So the cmake ... is the configure step, and then cmake -- build and then dot means build whatever's been configured in this location. And you see that it goes through the progress of building and linking this thing. And so now you have a program, and you can run it with /simplenet Fortran, and we see now that it's given the same result as we got in Python. Any questions? Yes.
So you said the tensor data is not copied.
Yes.
If you to plug it to a GPU, it can be copied to a GPU.
Okay, so yes. So the question was that we mentioned that there's no data copying. That's correct. On the GPU, you have to do a copy. Like there's no way for us to get the information from the CPU to the GPU without doing a copy. And so we've implemented the functionality to do that. if you have a model that has its input on the GPU and its output on the CPU, it will automatically do this for you. I mean, potentially, if you've got a GPU like a Grace Hopper that has a unified memory space, then maybe you don't need to do it, but we haven't actually tested that yet.
So it shouldn't depend on the kind of aliasing that modifying the tensor in place. On CPU RAM, you should assume it's going to change it on GPU as well.
No, not for the tensor, because you'll need to copy it onto the GPU, but with the model, it just happens automatically. Okay, so we will move on to the next part, and I'll give the microphone back to Jack.
Okay. So what I would do is zip through this relatively quickly because A, there's not too much code to be written, and B, we're getting a little tight on time. But the main purpose of the second exercise is, now that kind of you've done a lot of the legwork to see how you do this whole thing end to end, going from PyTorch to running a model in Fortran, there are some additional considerations that need to be taken when doing this in a more kind of practical setting, particularly when we're thinking about simulation codes, particularly Earth simulation codes. So the first one of these is, in contrast to what we've been doing here, which is where we read a net in, ran a tensor through it, looked at the results and closed everything down. In the things we're going to be replacing in numerical models, we're going to want to be running this code sort of hundreds, thousands of times over multiple iterations, multiple time steps. And there's a few kind of nuances to this. The main thing is that when we're talking about computational efficiencies, the most expensive part of all of this process is reading things in from disk or from where they've been saved. And that is particularly the model weights. So if you've got kind of a model you can imagine with several hundred, several thousand weights, if you're going to pull this in from disk every time you sort of do an iteration, every time you use that net, it's going to add up. And so there's more sensible ways of doing this, which is what we're going to talk about. And so what we advise, and again, there's an exercise that we're going to work through that's also included in the FTorch repo, is that instead you break things up into sort of 3 stages, much like you would do with traditional parameterizations in climate models. So you have kind of, firstly, there's an initialization where you set up the variables you're going to need, set up your model, read everything in from disk and store it in memory. Then you've got the kind of updating procedure, which is just going to be running that model that's already been loaded in, and you can call that multiple times in a row. And then the final stage, sort of as Joe went over in the previous exercise, is just some kind of finalization or cleanup, where we're going to destroy objects that were created in memory, make sure everything's nice and clean before we close the model down. So hopefully, if you've used any kind of large model codes before, that will be a familiar sort of process. So exercise 2, we're going to see this in practice. What this is going to do is take the simple net example we've already had, but instead of just running it once, we're now going to run it, I think, 10,000 times or 100,000 times, and we're going to kind of increment that tensor input with each iteration and store the results up and do a sum over them at the end. And we're going to do this kind of the bad way, just by taking the code from example 1 and doing it. And then we're going to do it the good way with this kind of initialization, reading in just once, updating every step, and then finalization just once at the end. As I say, I'll run through this. You can follow along, or you can just watch and go back in your own time. There's not much code to run. It's mostly kind of clicking through. So it might be more useful to kind of focus on looking at that. So, let me build on. If we go to exercise 2, you will see that there's the bad and the good. And if we take a look initially in the bad exercise, you'll see that from the main program, we make a call out to this ML mod. and you'll see that ML routine is a single subroutine in which we do exactly what we've just done, pull in the torch script file, create those tensors from our arrays, run it in forward mode, and then clean up everything afterwards. And so looking in the main code, you'll see that as part of our 10,000 iteration routine, we just call that entire thing in one go. Contrasting that, if we look at the good code, we now have a similar structure, but you can see here, before we call the ML routine in that loop, we've got this ML init initialization procedure. And after we do so, we've got this single ML finalization procedure. And you can see when we look at these in the module, I'll get rid of. Okay. You'll see that now this initialization procedure is taking care of reading in that file. The ML routine is just then using that loaded net to call the forward method at every iteration. And then the finalization routine is taking care of getting rid of things. And the reason this works, I should say, is in Fortran, if we define a variable kind of at the top level of a module, we can think of as a module of including not only subroutines or functions, but there's also variables or variables, parameters that are associated with that module, and they will persist in that module, sort of even if we've finished calling a subroutine that uses them, until we explicitly destroy them, as we do here. So any questions on that, or does that make sense to people? Super. So what we're going to do is generate the saved torch script model. So this is exactly the same as we did previously, just in another exercise. So hopefully if we run Python ptts, we've done that, we've output that .pt model. We can now build the two examples, the good and the bad example, again using CMake. So I'll do mukdir of build and go into that. We can now do CMake ... And as I said before, CMake's sort of very versatile. So here we're going to use it to build two executables, but just with one command. And then we'll actually execute that make file. And you'll see now within that folder, we've got the good and the bad example. So the first thing we'll do, as we said, we've got a net that we've loaded, and I think, if I remember, it's got 25 weights. So not much, sort of not compared to anything we're going to be using practically, but we'll see if we use the timing function that's built into Unix and run that bad example, calling that net, loading it at every iteration 10,000 times, takes a little bit. I think last time we did this workshop, it was about 16 seconds. I guess we can see if we've got a better or worse code space this time. There we go, about 16 seconds again. So, like I said, we're only loading 25 weights. So does anyone want to have a guess sort of how much that's impacting us? How long do you think it's maybe going to take to do the good approach? Aaron? 1 second? Yeah. Anyone else? Any guesses? Cool. Let's find out. So there we go. About half a second. So you can see this is just loading 25 weights. If you're loading a model with sort of hundreds, this is really going to hammer you. So don't do that. If you're going to deploy this sort of in a more practical setting, adopt this approach. Okay. So that's sort of all I've got to say. We've got 5 minutes left briefly at the end, where I think Joe maybe wants to say a little bit about AD. Yes.
Short question. Assume now maybe you emulate something like a source term in a letter code, and you have to call the source code then maybe in each quit cell.
Mhm.
So you have to call, maybe you have to load the data once, but then you have to call your neural network with maybe a small amount of data, but a lot time of stuff. It's
Mhm.
also not clear to me if this then maybe for Fortran is the best idea. Usually maybe assume what you usually do then in Fortran, you take a larger piece of data and do something and go back, maybe not vectorized, but somewhere in between. It depends a little bit on your machine or something like that. But here you have to call then all this machinery from your all the time again and again somewhere. Maybe the same what you do in maybe also with your source code. And then the next question is then you want to be this part on the GPU. It's also very not clear.
So in terms of the GPU, sort of that's beyond what we can do in an hour today, but there's a tutorial exercise in the FTorch repository. And there it's a case of, I think, but we had that specifying the device's Torch K CPU. It would be a case of changing the device that you specify there. So as long as you've compiled a library with the binaries for your backend, you could change that to, say, Torch K CUDA or Torch K HIP or Torch K MPS for Apple Silicon. And then that's the end of sort of what you need to do. We have the backend that looks after that. You don't need to worry about sort of calling the data transfer yourself. In terms of vectorizing your data, I don't quite understand. So are you saying if you were running with kind of MPI?
Yeah, maybe for instance, maybe you can say, maybe I have your source code and I run through the source code, maybe what you have written, and then you can say, okay, I do something like a broadcasting step. So I take maybe I run to the code, but I take already maybe 10 elements and do this operation for the 10 elements, this, and this. So I have to go through the code once, but I go not only maybe with this 5 numbers, but maybe with this 5 numbers multiplied by maybe a length of maybe 20 or something like that.
So you're saying if your net's trained to run on a single grid cell, but you want to run multiple. So the first thing would be it's something we're looking at the moment, but I believe because of its nature, because PyTorch wants to handle batching in operations, provided you provide the inputs in the sort of dimensions in the correct order, it's able to broadcast, sort of do that broadcasting implicitly. And so in some applications we've got at the moment, that's what we're looking at doing. And I think if you have a chat to Tom, there's a code that he's been working on recently that is designed kind of to operate on single atmospheric columns, but we want to pass in kind of a chunk of, as you say, maybe 20 atmospheric columns. It is possible to do this without doing a loop 20 times. So it will be the equivalent of kind of batching within PyTorch. If that makes sense.
Understand.
So yeah, I will briefly pass it to Joe
Sure.
to finish off.
Thank you. Yeah, so we're basically out of time, but there is another example which you could work through in your own time. For those of you that are interested in the the differentiable programming course, you can do automatic differentiation in FTorch. So we basically just expose the tool that PyTorch already has for this in FTorch. So there's an example where we work through a computation shown there. It's just a mathematical expression. We have 2 tensors A and B, and we can compute the gradient of dq by dA and dq by dP. The reason that we did this is, it's quite nice to see these expressions, but what is it actually useful for? Well, it's for online training. So this is the idea where you can actually not just do the training in Python, but then also load in a model that's potentially been pre-trained in Python and then fine-tune it in Fortran. So you don't need to save training data anywhere. You can just sort of every time you run your Fortran model, you can continue training the PyTorch model that you have. So if anybody's interested in that, then we can sort of discuss that later. but that's something that's a new feature in FTorch. We also support multiple inputs and multiple outputs, which is something that's mentioned before. We've talked quite a bit about GPU acceleration, and we support a lot of the major GPU hardware now. But if there's another one that you would like to use, then please let us know. Ongoing and future work, yeah, benchmarking is quite a big thing that we'd like to do to show that FTorch is usable at scale, and better integration into the community Earth system model and some other codes. There's a sort of demo of online training that I'm working on at the minute using UKCA, which is the UK's chemistry and aerosol model. So thanks very much for listening, and we'll go for lunch in the marquee, I think, today.